All right, so today we're going to do a review of limits in the Newton quotient. You should have covered this stuff in advanced functions. I know for some of you that was further back than others because I'm sure some of you guys took this last year. Can you guys raise your hand for me who took advanced functions like in their grade 11 year? Anyone? Okay, so there's quite a few of you guys. So this is probably a little further back in your memory for some people. Okay, can anybody tell me what a rate of change is? Michael.
Well, that's the rate at which something, generally a function in advanced functions, will change. So it's a constant, or it can be a dynamic rate of change, which changes. So the rate itself changes.
Yep. So if I'm looking at a line, for instance, we know that that has like one standard slope, right? So that has a constant rate of change. So essentially, like a rate of change is how quickly the y variable changes with respect to how the x value is changing. So okay, so a lot of times we measure like rates of change with the slope of a line. There's different lines that we use depending on what kind of rate of change we're looking at. So there are two kind of really big types of rates of change categories that we looked at in advanced functions. Does anyone remember those two different types? Essay? Yeah, awesome. So there's average rate of change and instantaneous. Okay, I'm just going to use ROC for rate of change. So average rate of change is going to be like over an interval of time. So it measures over an interval. Okay, we use the notation delta y over delta x for average rate of change. And we're measuring the slope of a secant line. So when I think about like a function, this is my function, and I'm measuring, let's say, from here to here, I actually want to know the slope of the line that connects those 2 points if I want to know the average rate of change. Okay, so this would be like a secant line. And the other one is instantaneous. This is measured at a specific point. Okay, to differentiate these two, we use dy over dx. Okay, so we're still finding the slope of a line, but we're basically, like if we see dy over dx, we're basically just saying, oh, it's instantaneous and not average. Okay, and this one will be the slope of a tangent line. Okay, so what that means is if I have a function again, and I want to know the rate of change, the instantaneous rate of change at this exact point, I look at the line that kind of just like skims the function right at that point, and I find the slope of that line. Okay, so we explored a couple different methods in advanced functions for how to find an instantaneous rate of change. A lot of them were estimated methods, which we kind of used like, okay, we can try to draw the tangent on this graph, or we can use this little chart and fill it in and see what the slopes are converging toward. So there's a couple different methods that we looked at. We could try, if we have a graph, to draw the tangent line. Okay, this is highly estimated because my tangent line might look different than Anita's tangent line. So if our tangent lines look slightly different, we're going to get slightly different slopes, and that's like very, very estimated. So this is like probably the most estimated way that you can do it. But if you don't know the equation of that specific graph, then this would probably be the only way that you'd be able to find instantaneous rate of change. We've used some tables before where we kind of shrink the interval between the x's, and we see what the slopes of the secant are getting closer and closer and closer toward. This was called a limit. So we find the limit of the secant slopes. Okay, and we also explored in advanced functions using the Newton quotient, or sometimes called Newton's quotient. Okay, so this is also the second point that I put here. This is also kind of an estimated method because we have to make a bit of a guess in that table. Newton's quotient is the only way for sure that we learned in advanced functions that we can actually find what that instantaneous rate of change is at that particular, at a specific point or in general for a function. So this one is more like a calculated method. So that was kind of like the highest method of finding instantaneous rate of change that we learned about in advanced functions. Okay, so your Newton quotient, we use dy over dx because that represents instantaneous rate of change. And we will say that's equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, so the aim of calculus, basically all of calculus can be proved with the Newton quotient, or it's the foundation of calculus. The aim of calculus is kind of to not have to use the Newton quotient, although it helps us prove some of the rules, but we're actually going to learn rules that allow us to not have to do the Newton quotient every single time. Because if you remember from advanced functions, it was like kind of a bit of a long process. So this method is great for proving some of those rules and saying like, yes, these for sure are true. But our goal with calculus is to learn some of the rules that are consistent so that we can find those instantaneous rates of change really quickly. All right. In advanced functions, we also learned about limits. You see a limit inside the Newton quotient, so it's also good for us to know kind of what that means. I also mentioned it up here. We found the limit of secant slopes. So a limit is some point in the domain of a function, okay, that the function's value approaches. So it's usually like we're approaching an x value of the function, and the limit is telling us what the y value is that's being approached, okay? So we call this, like if we're approaching a particular x value, we call this the argument. What is the limit approaching? That's the argument. And it's usually an x coordinate, okay? It's usually our independent variable that we're looking at. So we're gonna review some of the ways that we calculate limits. Okay, so we can calculate limits with graphs. We can also calculate limits with functions, so equations. And we can also calculate limits of things like even just lists of numbers. We can see if those have a particular value that they're converging toward. So the first one here is telling us limit as x approaches 1 of f at x. This whole graph here is f at x, both pieces of it. Okay, and basically what we want to know, what is y approaching as x approaches 1? That's kind of the question. So if we look at what is happening here, as I approach the x value 1, from either side, what are the y's getting closer and closer and closer toward? 0. So this limit is a pretty straightforward one. It equals 0. Okay, so the question you want to ask yourself is, what is y approaching as x approaches 1? Okay. Okay, limit as x approaches -2. So here's -2, that's up here. So as I approach that -2, what is y approaching? 3. So the limit is equal to 3. Okay, sometimes the limit will be equal to the y coordinate of that function, right? That happens a lot. Okay, anyone remember what this little plus represents for our next question? Essay? From the right. So what is the y approaching as x approaches 0 from the right? Okay? So this little guy means from the right. So if I'm coming from the right, I'm going from the right toward the left, right? Okay, so here is 0 for x, and I'm coming from the right, and I'm approaching 0. This one we might have to estimate just a little bit. What does it look like y is approaching as x approaches from the right? Yeah, like -0.5-ish. Okay, that one's a bit of an estimate, but it's okay. Okay, perfect. And then, of course, if the little plus that looks like an exponent means from the right, the negative must mean from the left. Awesome. Okay, so x is approaching -1 from the left. So I'm going to start toward the left of my graph, and I'm going to come toward -1. And what are my y's getting closer and closer toward as I approach -1 here? 2, that's right. It's approaching this point right here. Perfect. Now the second part of this asks me, what is the limit as x approaches -1 from the right this time? So I'm going to start from the right. And what are we getting closer and closer toward as we approach -1 here? -1, yeah. So we can see that they're kind of two different things, right? Yeah, Grayston? Yeah, so actually basically what this means is like as I'm kind of looking along my graph, when I hit -1, this point is actually undefined right here because it's a hollow point. The solid point is what the function is actually equal to when x is -1. So f at -1 is actually 2. Yeah. Okay, so what does this mean about the limit as x approaches -1? If it does not exist, and why is that, Alex?
Because the y values are not the same.
Right. So if the left and right limit approach two different things, I can't possibly decide which of those things is actually being approached because it's approaching two different things. So we say the limit does not exist. Okay, so the left and right limit must be equal for that limit to actually exist. Okay, and that brings us to the conditions for a limit to exist. So the right limit must exist, the left limit must exist, and the left and right limits must be equal to one another for that full limit to exist. Oh, sorry, guys, there's a little typo here. Can you guys remove, oh no, never mind. Just kidding, it's not. Don't remove anything. Yeah, so the limit as x approaches a needs to have those three things happening in order for the full limit to exist there. Right limit, left limit, and they're equal. Yep.
So we should be able to approach from both sides for one whole limit to exist.
Right, approach the same thing from both sides, yep. Okay? All right, so that's graphically. It's also true algebraically, these conditions, but sometimes we need to try some other strategies to evaluate limits algebraically, because I can't really, like, unless I want to graph the whole thing and figure out what's going on there, I'll probably need to use some other strategies for algebraic. So we are always going to try substitution first. Okay, and basically what that means is we're just going to try to take what the limit is approaching and plug it into the function. If I get a number that makes sense, then I'm good to go. Okay, so we'll use our judgment and see maybe if some of these things make sense or don't make sense. But the first thing that I'm going to try is I'll try to plug in -1 for x. When you plug in -1 for x, you drop the limit notation. Okay, so as soon as I plug that in, I don't need the limit thing anymore. Okay, and we'll just get 3 minus 7, which gives us -4. Is this a normal number? Is this okay? Makes sense, right? -4, it's fine. So substitution works in this case. And I'm just going to make a little note. You're going to drop the limit notation when you sub in. Okay, next one, we're gonna, yep, essay, sorry.
What happens if there's like a plus or minus x and x equal to negative 1?
Right, so sometimes what we'll do is we'll think kind of like a number line. So if I'm approaching, let's say 1 from the right, I might test a couple of values in there. I might say like, okay, 2 is to the right and 1.5, and then maybe I'll do 1.9 and I'll see what it's going toward. Okay, so we're gonna just try first to sub in 0 for our x's here, and we'll see if we get something that is acceptable. So I think we're getting 4 over 1 here, which just gives us 4. Is this okay? 4 is a normal number, we're good with that. Perfect. And notice that I dropped that limit notation out front here once I subbed in. Okay, so far substitution has worked well for us. Now I have the limit as x approaches infinity. Infinity is not a real number. It just is a concept, right? It just means we go forever toward the positives. So I can't really sub in with infinity, but I could do a couple little tests here to get maybe close to a really large number. So maybe we'll do a few tests. The first test, maybe I'm just going to sub in, let's say 1 million, okay, 6 zeros. So we're going to sub that into our calculators, and we'll see what we get here. If I were going toward negative infinity, maybe I would sub in something like -1 million. Okay, and we're going to use some good decimal place accuracy here, so I'll ask you guys, whoever gives me the answer, to give me maybe like a good amount of decimals that you see in your calculator there. Does anyone have it?
1.5, and then just zeros.
Oh, it has zeros after that? So it's like 0, 0, 0, something like that, right? And then,
Zeros, yeah.
oh, 4 zeros?
Yeah.
And then what?
325.
Okay, perfect. Well, we're doing a test, so we kind of want to have some accuracy to see what is happening, so I would recommend leaving a few. Okay, let's try another test. Let's say we try 1 billion, so 9 zeros this time. Gabby, what'd you get?
1.50000000003.
How many zeros did we say there? Was it 6? 7?
Yeah, 7.
And so on, right? Okay, so I think if we can kind of see a trend happening here. Every time I add some zeros onto this, I'm going to get more and more zeros here. So we could probably safely say that this is going toward the value 1.5. Agreed? Or in other words, 3 over 2. Okay, 1.5 is equal to 3 over 2. So we could probably take a pretty educated guess here that this is equal to 3 over 2. Now I want you guys to look at that equation of this function inside the limit here. Where do you see 3 over 2 in this function? Yeah, so we actually see it as like the ratio of the coefficients of the x's, right? So you guys can actually do this. Anytime you see, we actually took some time in advanced functions to graph linear over linear functions. Do you guys remember that? Not the people that took it maybe a year ago. But this 3 over 2, when I have a linear over linear function, the 3 over 2 is actually the horizontal asymptote of this function. So what you're going to notice about this is that you're going to have like those functions where you have the two little curved pieces. They look kind of like this. Okay, and this function has a horizontal asymptote right at 3 over 2. And basically what that's saying is if I go toward positive infinity, my y's are getting closer and closer and closer to this asymptote, but they're not touching it. But still the limit is approaching that because the y's are getting closer and closer and closer there. So that's kind of the idea. So anytime you see a linear over linear function, you can actually, and you're approaching positive or negative infinity, you can actually just use the coefficients of the x's. I mean, you can always do your tests as well if you're not 100% sure. But yeah, the quick way to do this is just to use those coefficients. You must be approaching infinity or negative infinity, though, for that to work. Okay. Last one. Let's see what happens when we sub in here. So if we sub in 3 in for all of our x's, we get 9 minus 6 minus 3, which is 0, and we get 3 minus 3, which is also 0. This is a form when we're evaluating limits that we do not like. This is called indeterminate form, which basically means we can't determine the limit at this point. Maybe we can do some math to kind of help us along the way, but right now I can't figure out the limit in the form that it's in. So does anyone remember what we have to do when we get something that's like 0 over 0 indeterminate form? No? Nicole? Yeah, so we have to do some factoring maybe, some canceling to try and get this into a form that will work for us. So I'm going to copy down the limit notation because this didn't work for us, right? So technically I'm not substituting in. I can't use that route. But we can factor the top. Two things that multiply to negative 3 add to negative 2 are negative 3 and positive 1. Okay, and then we can actually cancel here. And now we're looking at the limit as x approaches 3 of just x plus 1. Okay, once you feel like you've kind of simplified something at least in the equation, you can try subbing in again. And at that point, I'll drop the limit notation again. Okay, and now we actually can kind of see what that function is at least approaching as we go toward positive 3. And it's approaching 4. Okay. So essay, this was actually what you were asking me about. You said, what if we're like approaching from the right or from the left? Was everyone done with this? We're all good? Yeah? Okay. So essay asked me, what if it's approaching the left or from the right? Like, how do I calculate that? You should also notice, like, what's the restriction on this function here? X can't equal 2. So if I'm trying to evaluate a limit where I have a vertical asymptote, that's going to be a little tough, right? I'm probably going to get some problems when I try to evaluate this. If I tried to plug in 2 right now, I would get 6 over 0. And we know 6 over 0 is not a real number, right? So that actually should tell you, if you get number over 0, you're approaching an asymptote. Now, what happens when we approach an asymptote in a linear over linear function? Well, what's going to happen is I have an asymptote where x equals 2. That's because the bottom can't equal 2. Okay, this is a vertical asymptote. Horizontal asymptote is ratio of the x coefficients, which is 1. Okay, and what's going to happen? Yep. So 1 over 1. It's the ratio of the x coefficients, just like we did in this example up here. Okay, so what we know is I am going to have probably a function that looks something like this because the y, oh, actually no, sorry. The function is going to look more like this because it has a y-intercept at -4. And I know that because x plus 4 is on the top. The 0 of that is the x-intercept. So over here I have -4. And linear over linear functions are always mirrored on both sides. We have that, like, we call it a hyperbola. It has the mirrors on both sides. So what are we noticing about this graph as it approaches the vertical asymptote? What happens? It turns and it goes either down toward -infinity or up toward +infinity, depending on the way that we're coming, right? If I'm coming from the right or from the left. Now, you're probably saying, like, I don't know how to sketch this graph, so how do I do this, right? Or I don't remember how to. That's okay. You can still calculate this, okay? It's super helpful if you can sketch a little graph and then you can kind of see, oh, if I'm coming from the left, then I'm going down toward -infinity. But if you're not quite sure, you can always approach from the left numerically, right? So if I look at a number line, I have 1 and I have 2. And if I'm coming from the left, I can maybe do a couple tests. Maybe I can say, okay, we'll test when x equals 1, and then maybe we'll test 1.5, and then maybe we'll get a little bit closer. We'll test 1.9, something like that, right? So I'm going to come at 2 from the left. If I were coming from the right, maybe I would start with 3, and then 2.5, and then 2.01, or something like that, right? Maybe we'll test like 1.99. I already know, because this is some kind of asymptote that I'm approaching, it's going to be +infinity or -infinity. That's what's going to happen, right? I'm going to go either up forever or down forever. So all I really need to check with this is if I'm going toward the negatives or going toward the positives. And then I'll know positive or -infinity. So let's just do a couple little tests here. If I plug in 1, I will get 5 over -1, and that gives me -5. Okay, I should really already know it by this point, but we'll do a couple other little tests here. We'll test 1.5. Okay, we'll get 5.5 over -0.5, so I think that gives us -11. And then maybe we'll do one more. We'll test when x is let's say 999. We'll go really close to 2. This one I will need your help with calculating. Can't do that one in my head. Gabby, did you get an answer? Not yet? Great. So the guess is perhaps that we will get larger and larger negative numbers the closer we get to 2, right? So I should already really kind of know, I'm deciding here between positive infinity and negative infinity. So what's my choice? Negative infinity, yeah. Okay, I will always know I'm approaching a vertical asymptote if I sub in and I get number over 0. If I get 0 over 0, like over here, indeterminate form, it just means I'm approaching an undefined point. Okay, 0 over 0, I'm approaching some area that's undefined. Number over 0, like if I subbed in, we get 6 over 0 if you sub in. And that means I'm actually approaching a vertical asymptote. Okay, we're going to talk more on this again later. But yeah, just for your knowledge now. Okay, so number over 0, it doesn't have to be 6 over 0, of course, any number over 0. But in this case, it's 6 over 0. Yep.
You end up with 0 over 0. Does that mean you have to factor something out or get rid of something?
Yeah, so what that means is you're approaching essentially like an undefined area of the graph, so probably like an undefined point. And then that means that you're going to have to do some math work before you can actually calculate. This one, we can't really factor anything, right? Because it's just x plus 4, x minus 2, so we have to use another strategy to calculate. All right. Limits of sequences, we're just looking at what is being approached. So is this going toward some particular value? Yes, no, what is that value? So how about A? Is this approaching any specific, is this approaching any specific value? You say 1? Well, let's write out what would happen after this. 0.7, 0.8, 0.9, 1, and then what? 1.1. So is this ever going to stop? So what is this going toward? Okay, so the limit would be infinity. Okay, technically, if something is approaching infinity, it doesn't exist, right? Because I'm not actually approaching a specific value. It's just kind of like more of a concept. We're just saying it goes on forever. So you could also say this limit does not exist. Okay, how about B? Is this approaching like any particular value? Now, it doesn't ever have to reach that value. We're just saying, is it approaching? Is it getting closer and closer and closer to something? 1, that's right. Yeah. So basically what's happening, if you think about this like in a graph, I'm going like 1, let's say 0.9, and then 1 again, but then I'm getting closer to it, and then 1, and then closer to it. So every single time I go forward in this sequence, I'm going to get closer and closer and closer to 1, right? So think of those points getting closer and closer and closer together. So it doesn't matter if I ever reach 1 definitively. It's just saying what is it going toward. That's it. So 0.9999, and then 1, and then so on, right? So we're just going to keep getting closer and closer and closer to 1. Okay, how about C? 0? Do you guys agree? What's that essay? Negative infinity? What do you guys think? 0 or negative infinity? I think we're just going to keep getting smaller and smaller numbers, right? So like 1 over 32, 1 over 64, 1 over 128, and that value is just going to get smaller and smaller and smaller. So we are approaching 0 here. Perfect. Any questions before we move on to the next little section here? Kaylin, did you grab a lesson here?
Yeah.
Okay, so we're just in the middle of that right now. Okay, so the last thing about limits before we move on to the Newton quotient, a couple examples for Newton quotient, are we can figure out if a graph is continuous. Firstly, what does it mean for a graph to be continuous? What does this mean?
Does it like
That's good.
keeps going, basically?
So continuous is different than like the arrows on the end of a graph that continues, right? Kind of two different things. So it doesn't split. Can you unpack this for us a little bit?
Is it like break off like the one we're looking at with wire?
Right, so the very first graph that we looked at, this is called a piecewise function, and it has like a gap in the graph, right? I have to actually physically lift my pencil to get from one piece to another. If my function is continuous, I can trace along the whole function, and I don't have to lift my pencil. That doesn't necessarily mean it has arrows on the end, right? This is a continuous function. I can get from the left side to the right side of this without lifting my pen. But if I have something like this, let's say, even if it has arrows on the end, if it has a gap in there somewhere where I have to actually lift my pencil to get to the other piece, that's discontinuous. Essay?
With the graph that has the asymptotes and like going to be piecewise?
It's not really a piecewise function, it's just a function that would be discontinuous. Yeah. Piecewise kind of means it's made up of like two different functions together on the same graph. This guy is one single function, but it has some gaps, so it's discontinuous. Nicole?
If the graph has a hole, is it considered continuous?
Pardon?
So the graph has like a hole.
Yep, so that would be discontinuous. But what we're actually going to test is continuity at particular points on the graph. So if I have information about the limit, I should be able to, and information about the function as well, I should be able to decide if a function is continuous or discontinuous at that single x value that we're exploring. So I'm actually going to give you guys the answers for this, and you're going to tell me why I'm giving you certain answers for this. So this is asking what information you know about the limit and what information we know about continuity. So I'm going to say, I know the limit as x approaches 2 of the function f at x is equal to 3. So it exists and it's equal to 3. But the function is discontinuous when x equals 2. So why does the limit exist and why is it equal to 3? We talked about this earlier in the lesson. Kaylee? Okay, so the left one and the right one exist, and they are equal to the same value. Okay, those are the conditions for a limit to exist, and it's equal to what the left and right limits are equal to. Now, why is the function discontinuous when x equals 2? This gives us another little piece of information. What does this tell us right here under the conditions? So what does that mean in this scenario? What does it have to be equal to in order for it to be continuous when x equals 2? Alex? It has to equal the limit. So this is saying the limit must actually be equal to the function evaluated at that particular x coordinate. So if this is not equal to 3, I know the function is discontinuous at this particular x value. Okay? All right. Can somebody tell me what we know about the limit in the next one? Does not exist. Why? Perfect. So the left limit and the right limit exist, but they're not equal. That's a problem. So the limit as we're approaching that particular x value doesn't exist. Okay. What do we know about continuity when x equals 1? Is the function continuous when x equals 1 or discontinuous? Temmie?
Discontinuous.
Yeah. Why discontinuous? Alex?
Because there's no limit.
Yeah, so first, the limit has to exist. If the limit doesn't exist, then the conditions for continuity are botched, right? We have to have the limit existing at that particular x coordinate. As soon as that doesn't happen, it's not continuous at that point. Okay, so we say the function is discontinuous when x equals 1. Okay, what do we know about the limit in the last one? What can you guys tell me? So it exists and it's equal to 10. Okay, we have a two-way match here. The left limit and the right limit are the same value. That means the limit exists. It's equal to 10. Essay? It is continuous because the function evaluated at this x coordinate right here is also equal to 10. So we have a three-way match. That means the limit exists and it's also continuous when x equals -1. So this function is actually continuous. That does not mean that it's a continuous function everywhere. It only means at that particular x coordinate it is continuous. Okay, so there could be gaps somewhere else. We don't know enough about the function. It just tells us it's a function, some function f at x. So this is the most information I can get from that. Okay, so for this one, we need that three-way match. 10, 10, 10. Make sense? So all three things need to be equal for the limit to exist and for it to also be continuous. Okay, cool. So we're going to switch gears. We're going to do a couple examples in the Newton quotient. You guys will have a few minutes at the end, hopefully, to do a couple of your own questions. So Newton quotient allows us to find the equation for instantaneous rate of change for anywhere on the function we could possibly want to calculate. So we're going to use the Newton quotient to find the general equation for instantaneous rate of change. And once we have that, I can literally just like plug in x coordinates and I can find any instantaneous rate of change that I want. So the first thing that we need to know in order to use the Newton quotient, which is back up here, just as a reminder, okay, this is what we're going to use. Okay, I'm also going to give actually just a brief explanation here. This allows us to find the equation for the slope of the tangent line, or in other words, the instantaneous rate of change, anywhere on the function. Okay, so think of these two things as like kind of the same in your mind. Slope of the tangent line is telling us instantaneous rate of change for that function at whatever particular x coordinate we're calculating for. Okay, so slope of tangent line, instantaneous rate of change. Those two things are like synonyms almost. Okay, can I scroll? We're all good? Okay. Let's scroll back down. So in order to use the Newton quotient, I need f at x, and I also need to know f at x plus h. If I want to find f at x plus h, what is this telling me to do in my function? Where? Okay, so in place of x, I'm plugging in x plus h, right? So I'm going to get where this x is, I'm plugging in x plus h plus 1. So really I can just write it as like x plus h plus 1. That's what f at x plus h is. Okay? If this is a little bit confusing for you, I want you to think about what we do when we calculate something, don't write this, like x plus, or f at 2. Basically what this is telling me is sub in 2 for x, right? And so we know we replace all the x's in the equation with 2. It's no different when we do f at x plus h. I replace all the x's with x plus h, right? Same as what I would do for f at 2, I'm going to do for f at x plus h. Okay, now we're going to plug this into the Newton quotient. I like to kind of just do this off to the side first so that I can just plug it right in once we're ready to go. So we're finding dy over dx, or another way that you might remember having used in advanced functions is we do this f prime at x. Okay, and basically what this means is we're finding the equation for the slope of the tangent anywhere on our function, or in other words, the derivative of the function. Okay? All right, so this is equal to the limit as h approaches 0 of f at x plus h minus f at x, just recopying the Newton quotient from above. And then we're going to plug these things in. You are going to continue this limit notation until we have subbed in h equals 0. Any questions so far? So this is the Newton quotient equation that I wrote a few pages ago. Temmie.
What is that? Like f at x? What is that like notation for that?
So this guy right here,
Yeah.
this basically means the word is derivative. This is kind of what all calculus is about, but we read this f prime at x, or f prime of x. And basically it just means we're finding the equation for instantaneous rate of change. Okay? Now, usually what we talked about above is we sub in 0, or we sub in what we're approaching into our equation as like a first method. But I can already see if I plug in 0 here and here, I'm going to get indeterminate form because I'm going to have x plus 1 or the square root of x plus 1 minus the square root of x plus 1 all over 0. And that's going to be 0 over 0. So subbing in at this point is a bit of an issue. Now these ones are a little trickier because usually we kind of just like simplify and factor and we're happy with that. But this one, I can't really factor anything right now. I can't simplify anything right now. So we have to do a little kind of math magic here. Okay, so what we're going to do is we're going to kind of like try and see if we can create like something that's similar to a difference of squares. So difference of squares, if you can remember, is kind of like two things that are multiplied by one another, but they have two opposite signs in them. So instead of a minus, I'm going to put a plus. Okay? Now I can't just multiply something into the top of a fraction. I also have to multiply it into the bottom in order to maintain that balance there, right? So see how this one's minus? We're just putting the exact same thing but a plus there. And I also have to do that on the bottom. Okay, because I don't want to change the equation. I just want to add something in that still keeps the equation the same. This is technically 1 because I divide that thing by itself. I want to see if I can work with it a little bit differently. Okay, now I trust that you guys can FOIL. So I'm going to show you what the foiling is here, but I'm going to erase it after. If you guys want to write this somewhere, like if you have a space on your page, maybe up at the top or somewhere, you can. But again, I trust that you guys can probably FOIL this out. But I just want to show you guys. I'm going to be using this space after for the next one too. So, okay, we're just going to see what happens when we multiply here. So this times itself is that thing squared. So what I get is just what's left underneath the root. I just get x plus h plus 1. Okay, same thing times itself. A root squared, the root and squared cancel. Okay, then outsides, I'm going to get root x plus 1 times root x plus h plus 1. And then we're going to get a minus of that same thing when we do insides. So it'll be like minus root x plus 1, root x plus h plus 1. And excuse me, going on to the next line here, then we're going to get a minus root x plus 1 times root x plus 1 is root x plus 1 squared. So we're just left with x plus 1. Okay, now this is pretty cool what ends up happening here. The plus and the minus cancel, just like in a difference of squares when we FOIL that out. And then I have x plus h plus 1 minus x minus 1. And all that I'm left with at this point is h, because x minus x cancels, 1 minus 1 cancels. Yep.
Is there any way you could skip the middle part?
Pardon?
Is there any way you could skip the middle part and just do the first and last part?
Yeah, I mean you can because they cancel out, right? As long as it's like a difference of squares. But I'm just showing you guys why it cancels out, just so that no one's confused. Okay, so really what we have left on the top, guys, is we have h left on the top now. And I have h here. And then I have x plus h plus 1 plus root of x plus 1, right? Because we just FOILed this over here. Okay, we're going to try subbing in now. We're going to see, or actually we're going to cancel first. So there's 1 remaining on top. And then we're going to try to substitute in. Okay, so when I sub in h equals 0, I can drop the limit notation. And really what I have now is I have root x plus 1 plus another root x plus 1. So how many root x plus 1s do I have? I have 2. I have 2 root x plus 1s. So that's our equation for instantaneous rate of change. Sorry, I'll scroll up so you guys can see it. Okay, so notice as soon as I subbed in h equals 0 here, I dropped the limit notation that was out front. Okay, so always when you sub in for a limit, as soon as you sub in, you drop the notation. Okay, that one is a little trickier. We're going to try one that's a little bit more straightforward. But if you can do that one, you're well on your way. Just going to make some space here. Is everyone okay if I scroll to the last example here? Can someone say 1 second? Problem. Okay, so I'm just going to make a little note here just for our purposes to get from here to here. We FOILed. Good to go? Okay, last one. So, so what we need first, if I'm going to sub into the Newton quotient, is I need to know what g at x plus h is, which means that I sub in x plus h squared plus 3. Okay? Biggest mistake, even still in grade 12 calculus, is people expanding x plus h squared. X plus h squared is not equal to, what am I about to say? What is it equal to? What do we have to do? Yes, very good. So x plus h squared is not x squared plus h squared. I don't just put that exponent in there. I actually have to FOIL out x plus h times x plus h, okay? Which gives us x squared plus 2xh plus h squared plus 3. Don't be that guy that writes x squared plus h squared. Please. All right, so we are going to find instantaneous rate of change, an equation for it. And that means that we're finding essentially the derivative of the function. Okay, g prime at x is the notation that we use. Okay, and we're going to do that by using the Newton quotient again. So the limit as h approaches 0 of now g at x plus h minus g at x over h. Okay, and we've already found g at x plus h, so we can sub it in now. Okay, this one's going to be a little bit more straightforward than the last. And I'm putting g at x in brackets because every term in that needs the negative inside. Okay, so this negative will actually be distributed to every term in g at x or f at x or whatever function you're using. Okay, do I necessarily need you to write every single one of these steps? No. But write a few at least, just so I can kind of follow your train of thought. Okay, a lot of times what you'll notice when you use this method is like x squared and negative x squared, those things cancel. Positive 3 and negative 3, those things cancel. So you'll see a couple things cancel out. Okay, if I try to sub in at this point, I'm still going to get 0 plus 0 over 0, which gives me 0 over 0, and that's indeterminate form. Does anyone have any ideas of what we can do to get this out of indeterminate form? Temi? We're going to factor out the h, that's right. Okay, so common factor the h on top. There's an h here and an h here. We're left with 2x plus h all over h. And then the h's will reduce with one another. Okay, so basically what we have is just 2x plus h, and I can sub in 0 for h now, and I don't get indeterminate form. That's the goal. We don't want that. Okay, so drop your limit notation when you sub in that 0, and now we know that g prime at x, or the derivative, which is the equation for the slope of the tangent anywhere on this function, is 2x. Okay, now the great thing is with calculus, I can figure that out in 2 seconds. But we need to understand the Newton quotient in order to understand calculus, right? So that's why we're just reviewing this. But this is the value of calculus, right? Is that we can just be like, oh, it's 2x. Grayson? I may ask you to do like one Newton quotient question, if anything, but for the most part, we're learning the derivative rules so that we don't have to go through this whole process. Okay? It's still important to understand like the Newton quotient to understand where these rules come from. But yeah, calculus is so that we don't have to do this all the time. Okay? Okay, so we're going to try some questions. There is a limits section